Good day, class. So now this video will discuss on the third state of matter, or we know it as the gas or the gases. So gases, as chemically defined, has no definite shape and no definite volume. They have low densities and they are easily compressed. Gases exert pressure, and their behavior are explained by what we call their kinetic molecular theory. So, in explaining the behaviors of gases, we have four quantities or values to keep in mind. First, here is the amount of gas, which is symbolized small letter n. Then we have the volume, the temperature, and the pressure. So here, for example, the air around us exerts a pressure which we call your atmospheric pressure, and at 0 degrees Celsius and 1 atmosphere, these are designated as the standard temperature and pressure, which we call as STP. So STP simply means the pressure and temperature at which we call it the atmospheric pressure of 0 degrees Celsius and 1 atmosphere. So to further explain our gases, we have four laws that govern the explanation of gases and their behaviors. First one here, we have the Boyle's law, the Charles law, the Avogadro's law, and the Dalton's law. And then we have a special type of law that also uh, explains your ideal gases, which is called your ideal gas law or ideal gas equation, which is your P V is equals to nRT. And so your P is your pressure, V is your volume, N is the amount of gas, R is your gas constant, and then we have your T for temperature. The PVNRT or the ideal gas equation is derived from the four laws I have stated earlier: the Boyle's law, the Charles law, the Avogadro's law, and the Dalton's law. So before we proceed with the equation of each of those laws, let us first define the properties or the general properties of gases. Okay. First property of gas is that gases have mass. I see gas daw ay mayroong mass. Second is that gases are easy to be compressed. Ibig sabihin, gases are compressible. The third property of a gas is called or is stated as gases fill their containers completely. Yeah. So a volume of a container is filled with the same amount or volume of a gas. Fourth is what we call is stated the different gases can move through each other quite rapidly. So the molecules of gases moves through each other rapidly within its container or outside within the atmosphere. I have here the diffusion, which is the movement of particles from higher concentration to lower concentration. So basically, gases tend to diffuse within its area or its volume. The fifth uh, property of gas is that gases exerts pressure. Okay. Fifth, gases exerts pressure. And the last property of your gas is the pressure of a gas depends on its temperature. So therefore, pressure is related to temperature in dealing with your gases. So, for example, during hot summer days, the air in automobile tires exerts higher pressure, but as the weather gets cold, the air in the tires exerts a lower pressure, which causes the tires to flatten. So, we have an everyday example of how pressure and temperature are interrelated in dealing with your gases. So with that, we discuss now the kinetic molecular theory of gases. kinetic molecular theory of gases. So, the kinetic molecular theory of gases is a model that explains and accounts for the behavior of gases. It was the work of three outstanding scientists. We have Rudolf Clausius, James Clerk Maxwell, and we have also Mr. Ludwig Boltzmann. So, they have the following postulations on the kinetic molecular theory of gases. According to Clausius, Maxwell, and Boltzmann, the kinetic molecular theory has three distinct postulations when describing your gases. First one, a gas consists of a very small particles, each of which has a mass. So each particles of your gas contains a mass. Each molecule, because gases contains molecules, molecules are made up of atoms. So here, most of the particles of gases are molecules, and others are atoms, and they are very small for our naked eye to see, but they contain mass. Second postulation here of the kinetic molecular theory states that the distances separating gas particles are relatively large. So they are loosely. If you have solid particles that are compact and liquids are slightly compact, therefore your gases are loosely uh, separated from each other. And hence, these large distances allow gases to be pushed closer together, and so gases are easily compressed. Postulates on our first behavior of a second behavior of gases. Third statement, according to the three scientists, is that gas particles are in constant rapid random motion. So they are randomly. The molecules of gases are in constant rapid random motion, which explains why gases easily mix with each other and quickly diffuses throughout a container. Fourth statement, according to the KMT, is that collisions of gas particles with each other or with the walls of the container are perfectly elastic. This means that gas particles keep on colliding, okay, with each other and with the walls of the container without slowing down. We call it elastic collision. And here, it is in a perfectly elastic collision and no energy of motion is lost. For example, we have one particle here, another particle here. So when they collide, they have a perfectly elastic collision, and there is no loss of energy within these collisions. They just travel from their own distances. We call it your elastic collision between gaseous molecules. And the fifth is that the average kinetic energy of gas particles depend only on the temperature of the gas. So the kinetic energy of your gases or of your gas particles depends on the temperature of that gas. So gas particles have higher kinetic energy at higher temperatures and lower kinetic energy at the lower temperatures. So this is your fifth statement, and the last is gas particles exert no force on one another. In other words, attractive forces between gas particles are so weak because of their uh, loose distances. They do not condense into a liquid because they exert only very weak attractive forces upon each other. Those are the postulates of the kinetic molecular theory of gases according to Clausius, Maxwell, and Boltzmann. So this time, with the properties, behavior, and the postulates regarding to the kinetic molecular theory of your gases, we will now proceed to the measurements of gases. How to measure gases. Okay, again, let us move back here that our gases, to measure the gas, you have to predict the behavior and determine them according to the amount of gas, the volume, the temperature and the pressure. So in relation to the amount of gas, start with the first, the amount of gas. Okay, so in the amount of gas, this is defined as the quantity of gas in a given sample, which is expressed in terms of moles of gas. And again, that is moles of gas, the amount of gas. So to get the moles of gas, all you have to do is get the weight of the gas over the molecular weight of the gas. Example this one. For example, if we have 1 gram of helium, to get the amount of gas, all you have to do is you have N, you have the weight of the gas, which is 1 gram, over the molecular weight of helium, which is 4 grams per mole. So we have to cancel the gram units. You're left with the mole, which is exactly the moles of gas. All you have to do now is 1 divided by, we have 1 over 4 moles, and 1 divided by 4, that is equivalent to 0.25 moles. Therefore, in this example, 1 gram of helium has amount of gas of 0.25 moles of helium. This is how you get the amount of gas. Second is the volume. So the volume of gas is simply the volume of the container, because a gas uniformly fills any container in which it is placed. So if you have 1 liter container, that is or that has a volume of 1 liter of that particular gas. So that is how we measure your volume. So for temperature, so the temperature of a gas is usually measured with a thermometer, and the calculations involving gases should be expressed in the Kelvin temperature. And the Kelvin and Celsius temperatures are related by the following equation, wherein your degree Celsius is you simply add 273.15 to get the Kelvin measurement. You have to deal with the Kelvin first, involving temperature, because we are dealing with absolute temperatures. That is why any units in temperature should be first be converted to the Kelvin scale. And last, we have your pressure. So in pressure, the collisions of gas particles with the walls of the container result in a gas pressure. And every time a particle collides with the wall, it exerts an outward push or force on the wall. So the gases in a container, for example, will exert force onto the container to have your what we call your pressure. So the walls here are pressurized, or has an external or outward force from the gases inside. So here in pressure, we have your so-called atmospheric pressure. And one of the units used in pressure is the ATM. ATM, or simply atmosphere. So 1 atmosphere is equivalent to 101,325 Pascal or Pascal. Again, Pascal is another unit of measuring your pressure. So here are conversion units and numbers wherein you can convert one unit to another. In this case, we have atmosphere to Pascal, and 1 ATM is equivalent to 101,325 Pascal. Also, 1 ATM is equivalent to 760 mmHg, or also equivalent to 760 torr. mmHg, or millimeter mercury, mmHg, or millimeter mercury, and torr are another units of expressing pressure. Then you also have here 1 ATM equivalent to 14.70 pounds per square inch, or simply PSI. PSI is another set of uh, units for describing pressure. And last, we also have here 1 bar. A bar is also another unit measure for pressure. 1 bar is equivalent to 100,000 Pascal, which is also equivalent to 0.9869 atm. So here are our units for converting pressures of different units for this for converting different units to of your pressure. So we have your atms equivalency into Pascal, millimeter mercury, to torr, the psi. Then you have here the bar equivalent to 100,000 Pascal, equivalent to 0.9869 atm. So we have here again amount of gas, the volume. It simply pertains to the container, the volume of the container, temperature, the Kelvin scale, and the pressure at atm, which can also be converted to Pascal, mmHg, torr, psi, and bar. So with that, again, let me just say that the atmospheric pressure is not fixed. It regards to your STP. Dito. Okay? Atmospheric pressure is not fixed. It varies with the altitude of the Earth. And the lower the altitude, longer and heavier is the column of the air above the area of the Earth. That is why water vapor weighs lighter than the particles of the air. And with this, we start with our first law, the gas law. The gas laws, we have your Boyle's law. First law here, the first gas law is the Boyle's law. Boyle's law is also known as the pressure-volume relationship. Okay? It deals with describing the relationship between the pressure and the volume. And according to Boyle's law, the pressure and volume of a sample of a gas at constant temperature are inversely proportional to each other. Okay? So again, the pressure and volume of a gas at constant temperature are inversely proportional to each other. Therefore, mathematically speaking, P1 times V1 is equivalent to P sub 2 over V sub 2. Here is your Boyle's law. So take note that P is your pressure and V is your volume. Therefore, P sub 1 is your initial pressure, V sub 1 is your initial volume, and here P sub 2 is your final pressure and V sub 2 is your final volume. So if the three of the values in this equation are known, the fourth can be readily calculated. So paano? For example, let's say for example, a gas exerting a pressure. So there is a gas that exerts a pressure of 858 torr. So your gas is confined in a 5.00 liter container. Again, we have a gas exerting a pressure of 858 torr. That gas is contained in a 5-liter container. Now, the question is, what will be the pressure of the gas if it is confined into a 10.0 liter container? Here, what would happen to the pressure if your gas that is contained in a 5-liter container is transferred or confined into a 10-liter container. So we have here our given initial pressure of 858 torr, an initial volume of 5 liters, and a final volume of 10 liters. Take note that the initial is 5 because there is a transfer from one container, which is 5 liters, to another container that is 10 liters. So therefore, your 10-liter volume is your final volume. So take note that we also have the initial pressure because we'll be dealing with the pressure. And with that, we can apply Boyle's law. All you have to do is we will get to our equation. P sub 1, V sub 1 equals P sub 2 or times V sub 2. So what we're dealing here is we need to find the final pressure. So all you have to do is we have to release P sub 2 into the left side equation. All you have to do is we divide both sides by V sub 2. So we can release P sub 2. This becomes cancel. And your equation now is derived as P sub 2 is equivalent to P sub 1 times V sub 1 over V sub 2. V sub 2. All you have to do now is put your given numbers from the problem to the equation and you will arrive at 858 torr times the initial volume of 5.00 liters over the final volume of 10.0 liters. So in this case, we can cancel the liter unit and you'll have the torr, which is the unit for pressure. So all you have to do now is multiply these numbers from the numerator and divide it by the denominator. You will arrive at 429 torr. This now is your final pressure. So if you have any more questions, let's continue with our next law. We have your Charles law. Okay. Next one here is what we call your Charles law. Okay. So what is the difference between the Boyle's law and the Charles law? Boyle's law we have here is the pressure and volume relationship. On Charles law, that is the temperature and volume relationship. Okay, so we have here, according to the Charles law, at constant pressure, the volume of a fixed amount of gas is directly proportional to its absolute temperature. Absolute temperature. And so forth, we'll be using the Kelvin scale in determining the temperature. Again, Charles' law states that at constant pressure, the volume of a fixed amount of gas is directly proportional to its absolute temperature. So mathematically speaking, we can now use the equation that Charles' law is V sub 1 over T sub 1 equivalent to V sub 2 over T sub 2. Volume, initial volume again, T sub 1 is your initial temperature, V sub 2 is your final volume, and your T sub 2 is your final temperature at the Kelvin scale. For example, you have a balloon. We just draw a balloon here. So you have here your balloon. So this balloon has a volume of 1.75 liters. Okay, the temperature at which this volume is related ranged at about 25 degrees Celsius. So this balloon here at 25 degrees Celsius has a volume of 1.75 liters. The question here now, what will be the volume of the balloon if you take it out into the cold temperature of negative 20 degrees Celsius? Negative 20 degrees Celsius. Again, you have this balloon here, again, has a volume of 1.75 liters at this temperature, 25 degrees Celsius. Now, what would happen to the volume of this balloon if it's taken out to the temperature of negative 20 degrees Celsius? So now we can say that 1.75 liters is your initial volume. Your 25 degrees Celsius is your initial temperature, and your negative 20 is your final temperature. There's movement from 25 to negative 20. There's a movement of temperature. So all you have to do now is, again, before we proceed with the equation here, is first to convert these measurements of temperature into the Kelvin scale. All you have to do is add 273.15. Notice that arrives at around 298.15 Kelvin. And this one here is around 253.15 Kelvin. So now we have converted our temperature units and we have the initial volume. All you have to do now is use the equation here. So again, our initial volume, initial temperature, final volume, and final temperature. So what we're dealing here is that we're going to look for the final volume. So all you have to do now is, again, derive the equation, we cross multiply. So we have V sub 2 times T sub 1 is equivalent to V sub 1 times T sub 2. So we move again. Since we need to have this final volume, the left side equation alone, we not cross multiply. We divide both sides by T sub 1 to eliminate T sub 1 from the left side of the equation. So we have V sub 2 is equivalent to V sub 1 times T sub 2 over T sub 1. So we have the derived equation now. Based on our example, what we're looking for is the final volume. So, and all you have to do now is simply put your given units into the equation. So you have here initial temperature volume of 1.75 liters times the final temperature of 253.15 Kelvin and the initial temperature of 298.15 Kelvin. So we cancel Kelvin units. You will arrive at the liter, which is the unit for your volume. So all you have to do now is multiply again these numbers and divide by the denominator. You will arrive at around 1.49 liters. This is now your final volume. So therefore, sorry about that. Therefore, if you place your balloon from 25 degrees Celsius to negative 20 degrees Celsius, the volume will decrease from 1.75 to 1.49 liters. That is the temperature volume relationship of your Charles law. So again, next time I'll be having the next three equations on my next video. Thank you for listening, and if you have any questions, please feel free to contact your teacher. Thank you very much and happy learning.